All right, so we are still talking today 2.2 limits involving infinity. I just want to recap real quick yesterday one of the topics that we talked about, and that was what I have over here. We talked about horizontal asymptotes yesterday, right? And we talked about that a function would have a horizontal asymptote if the limit of that function as you approached either end, towards positive infinity or towards negative infinity, equaled some number. And if it equaled a number there, not an infinity or it does not exist, but it equals some number there, you have a horizontal asymptote at y equals whatever that number is. Remember, y equals being a horizontal line. Okay? So related to that topic, we're going to talk about other asymptotes, and that is vertical asymptotes. And vertical asymptotes are going to look very similar, so making sure that we know the fine differences between those. Vertical asymptotes are vertical lines, just like it sounds. And so that's why it says the line x equals. Remember, we talked about vertical lines are x equals a number. So x equals some number a for y equals f of x if one of these two things happens. The limit of our function as we approach a from the right is one of your infinities, positive or negative, or the limit of our function as x approaches that a from the left equals positive or negative infinity. So notice the difference between what we talked about with our horizontal asymptotes to where we're talking about our vertical asymptotes. This time we are approaching a number value, not the ends of our graph, but we're approaching some number value. And as we approach that, our graph is either going to start going up forever or it's going to start going down forever, is what this is saying. Okay, so if we sit these side by side here, you'll notice the small differences between them. It's still looking at the limit of our function, but this time x is approaching some number from the right or from the left. And as it approaches that number, our limit is going to either be positive or negative infinity. And if that's the case, the result is a vertical asymptote. And our vertical asymptotes are always at x equals, and it would match whatever number we were approaching. Okay, questions on that? Now, part of what you're going to notice as we go through today is going to overlap and go back to that section, and I know it's been almost a year since you've done this, but back in pre-calc when you learned how to manually graph rational expressions. Well, we went through factoring and looking for things that crossed off because that gave us a hole in our graph. Where do we find vertical asymptotes? Where do we find horizontal asymptotes? Where do we find our x-intercept, our y-intercept? All of that is going to help us out a little bit. And I'm going to fly through it. And a lot of times you'll have your graphing calculator as kind of an aid on this as well. But I do want to remind you of how we found those things. And I know this is going to seem really fast as I go through it. But I'm going to do that with this example, is remind you how it is we would have manually graphed a rational expression. So in our steps, we do find vertical asymptotes, which is what this one's asking us to do. And then all of the rest of it, well, all the rest of it is going to help me draw the graph so that I can answer the second question, describe the behavior to the left and right of each vertical asymptote. So first part of this is just getting our graph sketched. Job one, factor the function and see if anything crosses off. So if I look at this function and I factor it, looks like we're going to have nothing to cross off, right? And step number one was always looking for something to cross off. That would have been a hole in our graph. We don't have a hole in our graph. Step two, after we looked for a hole in our graph, was to find the vertical asymptotes, and that's kind of our focus today. Our vertical asymptotes, and these are side notes for yourself if you don't remember this, our vertical asymptote comes from what makes our denominator equal 0. Okay, so our vertical asymptotes are going to come from 2x minus 1 equaling 0 and x plus 4 equaling 0. Add 1, divide by 2, we'd have a vertical asymptote at 1/2. Subtract 4, we'd have a vertical asymptote at -4. In our picture, that looks like, let's see. dotted lines at 1/2 and -4. Okay. When we were graphing these, the next thing I would have gone to is deciding whether or not I had a horizontal asymptote or a slant asymptote, and that was all based off of little over big, big over little, or same, right? We are looking at a little over big, x to the first over an x squared, and so as we think about our horizontal asymptotes, that always led us to having a horizontal asymptote at y equals 0. Little over big, go back to what we talked about yesterday, right? Little over big. It's always going to flatline as we limit towards the right or limit towards the left. It's always going to flatline at 0. So we have a horizontal asymptote at 0, right at our x-axis there. The next couple things we looked at were our x and y intercepts, right? So our y-intercept, remember you're going to plug in 0 to find that. And our y-intercept on this one, if I plug in 0 to my function, I'd get 0 plus 3 over 0, 0 minus 4. We would get a y-intercept at -3/4. I just plugged in 0 to all the x's, and it gave me -3/4. So I would have a point at -3/4. My y-intercept, or my x-intercept, I get that one from anything that makes my numerator equal to 0. Our numerator is going to equal 0 at x equals -3. So it's going to cross my x-axis at -3. And then we just look for some points to help us kind of guide our graph. And in the middle there, we probably have enough points. My graph's going to follow the asymptotes and go through those points. So in the center here, my graph's going to look like this, go through my x-intercept, go through my y-intercept, follow my asymptote. On the outer sections, we really don't have any points to go off of. And so I would just pick points to test. And so I would probably test some extra points like test x equals 1. If I plugged x equals 1 in here, it's going to tell me if my graph's up here or down here, right? And if I plug x equals 1 in there, let's see, I would get 4 over 2 plus 7 is 9, minus 4 is 5. I get 4/5. So my point would be 1 comma 4/5. It'd be somewhere up here. And I'm not making these super perfect, but so we can kind of see. Same thing, I can plug in something all the way to the left of that graph to see if it's going to be a corner up here or a corner down here, like -5. And if I plug -5 in there, -5 plus 3 would be -2. Let's see, that'd be 25 times 2 is 50. Minus 35 would be 15. Minus 4 would be 11. So -2/11, which would be below. So this one's going to corner down here. Questions? Yeah. A horizontal asymptote can be crossed by your graph. The entire purpose of a horizontal asymptote is to show end behavior. So it really has nothing to do with the middle of our graph. The only types of asymptotes you can't cross are vertical and slant. Horizontal asymptotes can be crossed, and they can actually be crossed by any one of the pieces. All it's saying is as we get really, really far towards positive infinity or really, really far towards negative infinity, that my graph is going to end up kind of flatlining where that is. Other questions? Okay. Now, with that being said, I do think it is great for us to bring all this in, but can I grab my graphing calculator and type that in? If I know how to use my graphing calculator. And I would encourage you to make sure we know how to type something like this into my y equals, whether you can do that by a fraction or whether you have to type it in with parentheses because your calculator is an older version that doesn't allow you to type that in as a fraction. Know how to type this in and see that picture, okay? But it's also good for us to remember at one point, I know you guys all knew this because we passed a gateway last year on how to graph a rational expression, Okay. Now, the second question in this, we've actually answered the first. Find the vertical asymptotes. We did that first as we started. So you have your answers right here to find your vertical asymptotes. There they are. X equals 1/2 and X equals -4. Remember, of the format, X equals a number because they're vertical lines. The second question was this. Describe the behavior to the left and right of each vertical asymptote. So we should have to the left and to the right of 1/2 and to the left and to the right of -4. So actually kind of 4 answers right now. What does that mean? That means talk about the limits as they are approaching that number from the left and the limit as it is approaching that number from the right. So as I look at this, let's start here at -4. So the limit as X approaches -4 from the left, remember we put that little negative symbol up there of our function. So as I approach -4 from the left, our graph is headed down towards -infinity. So we would say from the left, it's heading to -infinity. From the right, as X approaches -4 from the right. So now I find my piece of graph here, and it's heading up towards positive infinity. And does that match with what I was talking about over here? As we are approaching a number, we're getting an infinity. That's how we get vertical asymptotes, right? So one or both sides of that asymptote should head to infinity. Same thing for at 1/2. The limit as X approaches 1/2 from the left. So from the left would be this piece of graph. As I approach 1/2, you can see that piece of graph is heading down towards -infinity. And as we approach 1/2 from the right, so from the right, I would be headed up to positive infinity. Questions on that? Okay, now when it asks you to describe the asymptotes of a function, we now know how to do that. There are 2 different types. We kind of have to think through which type do they have and how would I describe it, and this is how we describe them, right? Well, our description is the equation, and this is how they come is as our limits. All right, some trig vertical asymptotes that we need to remember. Describing vertical asymptotes for cotangent, cosecant, tangent, and secant. Sine and cosine don't have asymptotes. You'll notice this up here. Why do I have those grouped together? The reason I have cotangent and cosecant grouped together is if we were to look at those in terms of sines and cosines, you will notice that they share the same denominator, and the denominator is what drives our vertical asymptotes. So cotangent in terms of sines and cosines would be cosine over sine. Cosecant in terms of sines and cosines would be 1 over sine. Notice they have the same denominator. And again, it kind of depends on your pre-calc teacher since you guys are all coming from different places. But when you learned how to graph cotangent and cosecant, there's a good chance you learn to like dot out the denominator. Okay, so here's some good trig graphing review for you. When I graph a trig function, we typically put 4 marks out here and go out to 2 pi. That'd usually be 1 period of our graph. I would dot out my denominator. Sine curve start at 0, 0, go over to pi over 2, up 1, down to pi, down to -1, back up to 2 pi. And remember that this is your function values that you're looking at in graph form. And every single time that that sine graph hits my x-axis or my midline, it has a value of 0. Well, when I put 0 in the bottom of a fraction, I get undefined. And what undefined looks like on a graph is a vertical asymptote. So a vertical asymptote happens every time that sine curve hit my midline. Now the shape of those 2 graphs looks a little different between those asymptotes, right? If you remember, cotangent is the one that was like a little curve that decreased between your asymptotes, and cosecant is the one that looked like a parabola, right? But how can I describe these? Well, I can describe them as x equals and then where they're located. Now there's infinite number of them, so we kind of have to be generic. Your first one starts at 0, and then the distance between every single set of these is pi. They're pi distance apart, and they happen at every pi that you see. And so to represent that, it would be pi, and it's every pi I could ever come up with. And so to represent that, I just pick some scalar multiple k to say that any number pi, 8 pi, is going to have a vertical asymptote at it. Negative 5 pi is going to have a vertical asymptote. Any number that I can stick in here for k times pi would be the location of another vertical asymptote for those two functions. All right, same idea for tangent and secant is that, first of all, our denominators are the same. And that's why they have the same vertical asymptotes. That I would graph the denominator to find the location of those, because where my denominator is 0, it's going to be undefined. So if I were to dot out a cosine graph, remember, starts up at 0, 1, and then goes to my midline over at pi over 2. Down to negative 1, back up to my midline. And every place that that hits my midline, it is undefined, and all of those would then result in a vertical asymptote. These ones are just a little bit trickier to describe because they don't start at 0. So the first part of your description is where the first one starts. Well, I'm going to consider this one like our first one. And that would be to the right, pi over 2. So we would have start at pi over 2. The distance between them is still a distance of pi. So every one of them starting at pi over 2 is going to be a pi distance away, and it just matters how many pi distances I want to add to it to get me another asymptote. So it would look like plus any multiple of pi. Any k pi that I add to pi over 2 would land me at another asymptote for either tangent or secant. Questions on that? Okay, so using that on this next one, same question we just saw in the last one, asks you to sketch a graph, find the vertical asymptotes, and describe the behavior to the left and right of that vertical asymptote. The sketch of the graph is what's going to help us in looking at what's happening at my asymptote. So we just did this one on the last page. Remember, tangent is going to have asymptotes where cosine hits my x-axis. And then we'll give ourselves a quick reminder. Here's my dots for cosine. So my asymptotes are going to fall at my pi over 2 plus k pi. Okay, now the next part of it is, what does a tangent graph look like? Well, a tangent graph is the one that starts on my midline, exactly halfway between my asymptotes, and increases as I go, because tangent of like pi over 4 is up at 1. And it's the one that increases between my asymptotes. Cotangent is the same idea, but decreases between our asymptotes, right? And then secant and cosecant were the ones that look like parabolas. Okay, so let's answer the questions. Find the vertical asymptotes for the given function. We did that on the last page at x equals pi over 2 plus k pi. And then it says describe the behavior. We already have done a problem like this, but let's talk about, so the limit as our function tangent, as x approaches our asymptote, and I'm just going to say our asymptote, from the left. So pick one of the asymptotes in our picture, like, let's go this one right here. Start left of it and start tracing towards that asymptote. We are headed up, right? So as we approach that asymptote, we would be headed towards infinity from the left. As we approach our asymptote from the right, again, go to your picture, pick an asymptote. So if I pick this asymptote right here, start to the right of it, start heading towards it, we would be heading down towards negative infinity. Questions? All right, anyone still need this page? Okay. Next topic is what's called end behavior model. End behavior model is a basic function that has the same end behavior as the given function, and I can't stress basic function enough on this one. People try to overthink end behavior model, but what happens, guys, as we plug in massive numbers, and I'm talking about once we get into plugging in 1 million, 10 million, 1 billion, huge numbers, is your function will behave like the biggest exponent in it. And really, the rest of it is so small at that point compared to the rest of it that it's negligible. So an end behavior model, if this were our function and it's this big polynomial, it's really, once we get to the really big numbers, the far ends, is really going to behave like the biggest term. So its end behavior model would just be the biggest term. So some examples here, if I have fractions to look at and I'm asked to describe the end behavior model, what I'm going to do is go take the largest term from the numerator and denominator and simplify that ratio. So if this were my whole function, its end behavior model g of x would be the simplified largest term numerator denominator, 2x to the 5th over 3x squared, which actually can simplify further, right? Because I can take an x squared out of the numerator and the denominator and simplify it down even farther. This thing, as we get really far to the ends, end behavior, is going to behave like 2/3 x cubed, or 2x cubed over 3. So don't make end behavior harder than it needs to be. Same thing on the next one. Again, I go find the largest term from the numerator and the denominator, and I simplify that. So I'd be looking at 2x cubed over 5x cubed, and if the numerator and denominator are going to grow at the same rate, those will simplify. My x cubes will simplify out of here. This, as we go to the far left and far right, is going to behave like the fraction 2/5. It's going to flatline at 2/5 on both ends of our graph. So what basic function could describe your biggest term is what it's doing. Any questions on end behavior model? All right. Last one I just want to touch on is our exponential functions and how they relate to asymptotes. So end behavior on our exponential functions, a common exponential function to work with is e to the x, but this would also be any exponential function. So another example would be like 5 to the x, right? That's an exponent. E is just a number. 5 is a number. Those would behave the exact same way. Sketching a graph of an exponential function. First of all, I'll remind you at 0, if I plug 0 in here, 5 to the 0 or e to the 0, anything to the 0 is 1. So this would be up at 1. 5 to the first or e to the first is going to be pretty big, 5 or 2 point, whatever e is, 2.7. And then the reciprocal of that would be like 1/5 or 1 over e. But think about this. Can I ever plug something into my exponent, 5 to the x, e to the x, plug something in there and get a negative number as an answer? Never. So this is going to get really close to, but never actually get to 0, right? It's going to go through those, and then it's going to get really big really fast. So then talking about our limits, as we head to the right-hand side of that function, it just continues to get really big really fast, right? So it's going to go up to infinity. Is that a vertical asymptote? No, because we're not approaching a number, right? We're approaching an infinity. Don't get those two confused. The second one, as we approach negative infinity, is getting really close to 0. Now 0 is a number, and we're approaching an infinity. That gives us a horizontal asymptote. So asymptotes for our exponential functions, we have one. It is a horizontal asymptote at y equals 0. Questions? All right. Your assignment, let me explain the assignment just real quick. It's on page 77, and then it has this little thing that says APQQ. At the end of that, you're gonna see kind of a separate little box area that says AP Quick Quiz. That's what that's referring to. And on that one, you're doing 1 through 4, but on 4, you're just doing A, B, and C, not part D.